Science labs are a transformative model, similar to cloud computing. They provide least access to remote science lab facilities rather than locally provisioned school lab equipment. They also provide a powerful complement to hands-on labs and simulations. Through the use of remote online labs, students have direct control of real experimental equipment accessed through the internet. Students can use these labs, and with the use of remote online labs, students have direct control of real experimental equipment accessed through the internet. Students can use these labs anywhere and anytime from anywhere in the world. Remote online labs are not virtual laboratories, and they're not canned experiments. They are actually authentic laboratory experiences. Students can remotely manipulate instruments such as Geiger counters and spectrometers that might be housed at a university on a different continent and that are unlikely to be found in high school classrooms. I'm now going to show you a short video that will give you a demonstration of our remote lab.
The concept behind it is students from anywhere around the world could go online and they could access an instrument remotely. So they're able to pick the variables that they want to change. They're able to set the parameters of the experiment and go through the process of scientific design. It's not a virtual lab, it's not a canned lab, it's not a simulation. You can see the instrument moving, you can watch your experiment running, and the kids are fascinated by it. My students right now are working on a radioactivity lab where they access a Geiger counter in Queensland, Australia. And what they're studying is actually nuclear chemistry and the effects of gamma rays and beta particles and alpha particles. But we do it under the subtext of, is your cell phone going to fry your brain? Now, a cell phone doesn't release gamma radiation. It actually works using microwave radiation. But what they learn is that all electromagnetic radiation acts in a similar way, that intensity is proportional to 1 over distance squared, which is a very fancy mathematical way of saying the farther you step away from the source of radiation, the less intensity you're going to receive.
The lab starts with an interactive flash simulation that allows the students to see how the device behaves by moving it up and down and visualizing how the radioactive particles hit the Geiger counter. They can also get information and additional readings over here. For example, they could ask how's radioactivity measured, and they can get a reading on Geiger counters and how those measure radiation. Moving on, the student lab journal prompts the students for various questions and feedback. So here they need to write their research question. How does the intensity of radiation change as a function of distance? Next, I click Design phase, and we're going to save the information to the server. Now the student needs to design their experiment. So I'll pick a short distance, say 30 millimeters to measure radiation at, and a distance that's further away, say 60 millimeters. And I'll measure for maybe 3 seconds each time. I'm not really sure if I'm a student. And I'll repeat it 2 times. Then the lab journal asked me, why did I want to choose these distances? And so I'll say, well, I wanted to try some close by and far away, and 3 seconds seemed like a good time to start with. I'm not really sure. So next I click Investigate. My lab is then sent over to the device in Australia. I'm the number 1 in the queue. I've got about a minute left, and now I can switch over to a live webcam view of the device. Here's the Geiger counter on your left. There's a turntable that's going to spin the radioactive materials underneath. You can see the Geiger counter tube now moving up to my 30 millimeter distance that I typed in, taking the measurements, and then it's going to store all that data on our server for the students to then analyze later. Now you can see it's moving up to the 60 millimeter distance that I typed in. Again, it's going to collect the data. In the meantime, I could log off if I don't want to wait for it, or I can come back here and finish the prompt on my journal here. What is my prediction about what will happen? What do you think you'll see? And I'm going to type in, well, I think the intensity will go down the further away the Geiger counter is. In the meantime, the data is being sent back to the server, and if the student wanted to log back in, they would come back immediately to this screen here and pick up where they left off, so there's no need to wait. Once the data comes back, I'll be able to analyze it either by exporting it to Google Docs or Excel. So I can click here to export it. Or alternatively, I can use the built-in graphing tool that we have. So looking at my results, I can see that they do go down, but also they're a little bit different. So I'll write my initial observations are that the counts went down by about half, but each trial is different, so I'm not sure which number is right. So next I'll go ahead and fire up my analysis tool, do some graphs, insert those graphs in my lab journal, and then at the final question I'll explain that I think the relationship looks like a linear relationship with a negative slope, and I'll say, well, I'll probably want to run the lab again to see if the values I get keep changing. Finally, at the end of the lab, I can download a PDF, and then I can turn that in to the teacher to complete my assignment.
The students set up the scientific design by themselves at home. We do not do it in the classroom, which provides a lot more time to work on other curriculum. They run their labs after school, at night, 3 in the morning, whenever they want to, and come back the next day. We do peer review, which is something that you rarely ever get in a high school classroom, where they actually get to collaborate and talk about their results and decide, was your data better than mine? What did you try to work with? What were your variables? How many distances did you select? And maybe why was yours better than mine? There's not one right answer, but the students really get a chance to talk about maybe where the weaknesses were in their experimental setup. Then they go back home again. They work on a second run of the experiment, and what we're seeing is their scientific design dramatically improves. The fact that they got to do peer review and the fact that they have a lot of time at home, not a 50-minute class period, but a lot of time at home to think about how to design a really good experiment. We've seen the proof through studies that they're picking more distances to check, they're looking at greater time periods, they're running more trials, and they're doing better science.
So after we developed the radioactivity curriculum, that you just saw Tanya talking about, we conducted a pilot test of the radioactivity lab. We included 20 teachers and about 1,000 students. The students were in 5 different schools in 5 different states, in both face-to-face and online classrooms. They were in grades 8 through 12 in a variety of subject areas, from physics to chemistry to AP biology and environmental science. When we looked at our results, we actually found some significant gains in both process and science content learning. In particular, we found that lower performing students, based on scores on a pretest we had administered before conducting the radioactivity lab, demonstrated the greatest gains in the post-test. And the results are significant in process and content learning, even if you don't segment the students by performance. Only 4.6% of students who conducted iLabs in class conducted 3 or more experimental runs. A significantly higher percentage of students, about 12%, conducted 3 or more experimental runs outside of class. A significantly greater percentage of students conducting 3 or more experimental runs outside of class indicates that the flexibility and access provided by the remote online labs does in fact afford students a greater opportunity to engage in scientific inquiry. After the webinar, I invite you to use the Vimeo link that's provided in the window here to view a short clip that documents student engagement in the Remote Labs Network. If you have any further questions about remote online labs, I welcome you to email me at m-waldron